This is a tiny rod of glass inside a sheath of plastic to stabilize it. The glass inside has a tiny diameter, about 1/10 the size of a human hair. So in order to get my laser light into this tube, I need to focus this laser light. See how big that is? Way bigger than 1/10 the size of a human hair. So I need to focus that all down into a very small diameter. So I have a lens on this one that focuses the laser light down. So it's spread out here, but that's because it's past its focal point. The focal point is right to where it exits the laser right there, a very small focal point. So if I plug this into my long glass tube, watch what happens. I get a laser light coming out the end of it. Look at that. Think about how many reflections it's going through this entire cable. It's bouncing off that tiny little hair of glass all the way through this. And because it's almost perfect reflection through this entire thing, I get about the same brightness of light coming out of it that I'm putting into it. Once it's inside, the light's locked in there. It can't escape because inside it's coming at such a shallow angle, total internal reflection occurs and keeps the laser light locked inside of it, as if it were a perfect mirror that it's hitting on the outside. Now for some of you, this might not be that surprising to learn, and you might even recognize what I have here. This is simply a fiber optic cable. These are used all over the place in place of electric wires. You can send light through the cable instead of electricity, and then you can convert that light signal back into electricity to be used by computers. So I'm going to use this to convert this light signal into an electrical signal. So I turn on my laser here, you can see I have it coming out the end, and I'm just going to plug this into here. And I'm going to measure the voltage on here. So I get 0.39 volts. So you can see I'm turning this light signal into a voltage. On, 0.39 volts, off, 0. One of the downsides of fiber optic cables is that since the light has to bounce off the core at a certain angle, they can't bend too much. So it can easily curve around inside of this cable, but not if I bend it too much. See, the light escapes from it now because we're not past its critical angle now, so it can just exit the glass. There's no longer perfect internal reflection. You can see it very clear if I just show the center plastic part directly around the core. So now I've stripped away the outer coating. So now I just have the plastic sheath with the glass core right inside of it. Look how weird this looks. It suddenly just lights up when we give it any significant bend. This is so cool. So as long as you don't bend your fiber optic cables too much, then you can basically have a perfect surface to continually reflect the light through it. But then that leads me to my next question. What if you just shine some light in a long loop of cable and then removed the light and connected the two ends together? Would the light just continually go around in a circle forever, so you essentially trapped light inside of the cable? So I can connect both ends of these so that I have a complete loop now. So what if we were to trap all the light inside of this loop? Okay, I've got light coming out of the end. Now I'm going to hurry and take it off and plug it in. I get it? Well, the first problem with doing this is in the instant that I disconnect the light from this end of the cable to connect the other end, then the light's already exited the other end. Because I don't know if you've heard this already, but light moves really fast. So there's no way I can move fast enough to connect the other end.